So our next speaker is definitely the hero of this meeting, because Ang Lee came in, and he came in half an hour early. And I do believe half an hour early for him meant that he joined the meeting at 3:30 in the morning, which is truly impressive. So, and we are about to have a real delight of a talk, because I had the fortune of meeting Ang Lee when I was visiting China, and the breadth of the total synthesis work he does is absolutely fantastic. And so he covers all chemistry, but now and then he throws in some wonderful CH functionalization examples, and hopefully we might see some of those in today's talk. So just to tell you a little bit about Ang Lee, so he did his BS degree at Peking University, and then and I didn't realize this, but it makes perfect sense. He then went to do his PhD with Professor Casey Nicolau at Scripps. And obviously, through those two experiences, developed his love for total synthesis. He then began at Shanghai Institute of Organic Chemistry, which all of us know is a fantastic place to do research in organic chemistry in China. It's really the top place. And there he started in 2009, 2010, I believe, and has developed a fantastic reputation, and it's going to be a delight to hear your talk. So the title is going to be Natural Product Synthesis Using CH Functionalization. So welcome, and thank you for joining us at such an antisocial time as far as you were concerned.
Thank you so much, Hugh, for this very warm introduction, and I would also like to thank you for this invitation, and Rio for all the help. Today I'm going to share with you some examples of natural product synthesis using CH functionalization. We don't develop too much new chemistry in this area, but we really try to use these powerful tools to streamline complex molecule synthesis. So the story actually started from making aromatic compounds. So the conventional strategy, as almost all the undergraduates knows, is a so-called modification strategy. So you start from a suitable aromatic starting material, and you probably try to use different type of chemistry to put substitution groups on it. For example, you can do halogenation, put a bromine on it, and do cross-coupling. And of course, you can use very old-fashioned Friedel-Crafts chemistry, and in many cases work very well. But in these cases, you have to consider about the electronic effect of the substrate. Sometimes pretty hard to put on a functional group in the position desired. So then we think about an alternative strategy. Actually, many people use this before, but we found actually we can systematically use this strategy, so-called construction strategy, to make multiple substitute arenes. For example, benzene with 4, 5, or even 6 substitutions on it. So we can build a triene precursor, as shown here. And we install all the substituent group, and also put all the stereogenic center around this triene system, and then run the 6-pi electrocyclization, either promoted by light or just by heat. And we form this 6-membrane, and we don't really care about the stereochemistry, and we can oxidize that into a aromatic compound. So basically, these two strategies are both very powerful and sometimes could be complementary. Okay, so I will start from the second strategy. Shown here is a natural product called diphenolene. This molecule contains a tetrasubstitute benzene. As you can see here, the stereogenic center and also the substitution pattern around this aromatic ring is quite complex. So we think maybe we can start from a triene like this, and hopefully we can form a CC bond here. So that's the very basic idea. So the chemistry is like this. So we first prepare a trans-triene system through a Suzuki coupling. We get this intermediate and we enrich this compound with light. I summarize this double bond from the trans geometry to the cis geometry. Also in one part, the light also induce the 6-pi electrocyclization to give us compound 11 with this congested 6 membrane in here. And after that, we can treat this compound in the presence of DBU and oxygen. Presumably DBU can deprotonate this position to form an enolate, and that species could be oxidized by oxygen to form the corresponding peroxide and then undergo elimination to give us this aromatic compound. So basically this chemistry has nothing to do with CH functionalization, but shows the alternative way for us to make a tetrasubstitute arene. And after that, I just briefly show how to finish up this synthesis. So Sagusa-Ito oxidation gave us this enone species, and radical cyclization gave us this 7 membrane here. And after hydrogenation, decarboxylation, we get this advanced intermediate with this amide and ketone here, and reduction gave us this net product. So basically, we found this arene construction strategy is quite useful. So we move to another synthetic target, the X-myosin and R-myosin molecules. So you can see these molecules contain a very interesting carbazole motif, and this area, this aromatic ring has 4 substitution groups on it. And these molecules also are slightly different in terms of the stereochemistry at carbon 16. Some of them has this carboxylic acid at the equatorial position, and some of them have it at the axial position. So we think we can probably make these molecules through 2 different approaches. For example, the first one is the 6-pi electrocyclization approach, as I shown previously. And if we can build this triene, maybe we can form this CC bond here and make this carbazole smoothly. Alternatively, we also think we can start from this indole species. If we can activate this CH bond here, then, for example, we can form the palladium species by activating the CH bond and then push a hex cyclization to work and give us this carbazole species. So that's basically also very interesting to explore. So I would like to mention, the other players in the area of synthesis of these molecules, for example, Baron, Crichet, and Troiter. So the first strategy is pretty straightforward. So we prepare this declene transdeclene intermediate 14 through titanium radical cyclization, and then we oxidize the primary alcohol into the corresponding aldehyde, and Grignard reagent addition to this aldehyde, we get a secondary alcohol, and dehydration, we can make this triene. And we heat this triene at 120 degrees in the presence of air. So the electrocyclization aromatization proceed very well to give us the corresponding carbazole directly. And you can see the cell group is automatically deprotected under these conditions. And other functional groups, for example, the beta ketoester here is stable, and the bromine is also, the arobromide is also stable under these conditions. So then we move to the second strategy, which is related to CH functionalization. Actually, there are a lot of reports, very elegant studies in the literature, and many players' names are shown here. I must have missed some names in this area because so many people did a very nice contribution here. We try to active this CH bond highlighted in red, and hopefully we can do hex activation here. So particularly, I would like to mention my senior colleague, Professor Xian Lu. In 2006, he reported a very nice method study to use fairly simple indo with the olefin substituents and make the carbazole in one pot. So we borrow his conditions here. You can see palladium-2 and benzoquinone. In one pot, we can convert this indo species into the corresponding carbazole. Of course, the preparation of this indo precursor is also from the titanium chemistry. So we first get this epoxide and we open it up and to form a radical here. And this radical will attack this tri-substitute olefin and then further attack this the other olefin to give us this transdectin system. All right, so this study basically shows the power of indo-CH functionalization. So you don't have to prepare the triene, and you just take advantage of the reactivity of this indo-C2 C2H bond. So of course we can use this intermediate to push further to do the CN bond formation to make this dimer dioxamycin C, and also we use this intermediate, another intermediate to further functionalize to make this compound artemisinin B. And interestingly here we use another CH functionalization, which is methyl CH oxidation. So this chemistry is from Melanie Sanford. We first convert this ketone into the corresponding oxime, and then palladium-2 iodine-3 reagent can oxidize this methyl selectively to give us this acetate. And I would like to mention this the advantage of this oxime chemistry. Although this ketone is quite hindered, but the oxime formation is still very efficient, and the oxime substrate is quite stable under these conditions. And of course, to remove the oxime is sometimes could be a challenge. Here we use strong acid in the presence of acetone to remove the hydroxyamine, and then reduce the ketone into the corresponding secondary alcohol, hydrolyze and they protect these protecting groups give this net product. So in the synthesis of this molecule, we use the 2CH functionalization chemistry. Also for this Sanford chemistry, I'll show another more complex molecule synthesis in the end of this talk. Okay, so I would like to continue my talk with this second example of endoterpenoid synthesis. So this class of molecule is probably is quite familiar to many people. The Tabindo family is many synthetic chemists did very nice studies as shown here. And also we become interested in these molecules because very nice biosynthetic proposal by Richard Moore, the chemist who isolate these net products. So the idea is like this. So chlorine plus could active this electron-rich olefin, and then this vinyl indo species could attack this this position to form CC bond here intermolecularly, and at the same time it end up with carbocation species at the benzylic position of this indo. And we are very interested in the reactivity of this intermediate. Potentially, they can be you can view this intermediate as this conjugate imine, and potentially it can undergo a Prince type of microaddition to form the six-member ring and generate a tertiary carbocation species at here. And if this proton eliminate to form this double bond, you get this basic skeleton of happy indole. And of course, you can imagine a Friedel-Crafts reaction between this carbocation species and this indole C2 position. Then you will end up with the Fischer indole scaffold. And if you have some, or nature have some method to control the positional selectivity to do the Friedel-Crafts reaction at the indole C4 position, then you will generate this type of a hyperindole skeleton. And also, if you are familiar with a more complex molecule, a class of more complex molecule called ambiguins, then it's just contain a substitution at the indole C2 position, normally a reverse perennial group. So basically, we are very interested in this Prince type of Michael addition, and we think about probably we can do a formal CH oxidation Prince cyclization. So we can prepare a linear precursor like this, and if we can oxidize this indole benzylic position, although it's not a real CH functionalization, but we can formally functionalize this position and form this ring. Also generate these two stereogenic centers in one pot. So we try this reaction with DDQ, and it's very lucky for the first trial, we just obtained this desired product. And we optimize conditions. This reaction proceed quite well. In DMF 80 degree, we get 55% yield of the desired product. As a single diastereomer, this methyl stereochemistry control the stereochemical outcome of these two substituent group through presumably through all equatorial chair-like transition state. And you can see the substituent group. Basically, we can form a series of different compounds with a similar skeleton to the natural products, and also 5-member formation is also possible in this case. And we can have a substituent group on this aromatic ring, for example, methyl here, and reverse perennial group and here, and the stereochemical outcome could be confirmed by these X-ray structures. Okay, so the oxidation, so sometimes we need to add a scandium triplet. We suspect it can activate the DDQ, and this indole species can attack this DDQ in this way, and then further undergo elimination to form this conjugate imine species, and then this olefin attack here to generate the 4-membrane. To generate the 6-membrane. And we didn't observe this 3-membrane opening product. We didn't see the radical clot products, so which is also provide some evidence for this type of working model. So we quickly test this method into this formal CH oxidation method in the synthesis of these two molecules, happen to Q, and this is net part 4. And we just use different boronic acid starting material and use the chemistry developed by Kobayashi and Zembo. We can make this homoanalytic amine species 31 and 33. And these basically just a pair of diastereomers, and we can convert these compounds into the corresponding substrate and then do the one-pot oxidation cyclization to get this, these two net product directly. We can also change the cyclization conditions a little bit. For example, we can swap the solvent from DMF to DCE, and in the DMF conditions, we'll end up with this olefin substrate. So the carbonic ion just undergo proton elimination. But in here, when we use DCE, we can push further to have this Friedel-Crafts reaction work to form another 5-membrane here, and also excessive amount of DDQ will oxidize this position, the benzylic position, to form a double bond here. So from this linear precursor, we can just do 1-pot oxidative cyclization, Friedel-Crafts, and then full oxidation to give this compound 7 in one pot. And also, we also see a quite interesting structure from this family. This is the original proposed structure. If you look at this structure more carefully, so first it's quite interesting because it has a carbazole, which is kind of relevant to the our previous study. But here, if you look at more carefully, the position of this methyl looks quite weird. Normally, the Habindo family will have this isopropene group. So the methyl should locate it at this position, but not here. So we can't really imagine this methyl can automatically walk from here to here without a particular reason. So we think it could be a misassignment of the net product structure. So we guess the real structure, it's just a guess at that time, we guess it could be like this. So we happen to have a very quick route to synthesize this compound. So start from this aldehyde, the Nozaki-Hayama allylation chemistry to give this linear precursor very easily, and then DDQ oxidation from this compound 18, and then we use this CH functionalization chemistry again, palladium-2 and benzoquinone in one pot. We get 50%, more than 50% yield of this carbazole. We get a crystal structure of this compound to determine all the connectivity and the stereochemistry of this benzylic alcohol. And after that, we just activate this alcohol with Lewis acid and introduce this cyanide here. So here, once we get this compound, we can compare the structure, the 1D and 2D NMR spectral with the net product. We find it's perfectly matched the net product. So we revise the structure of the net product using this CH functionalization chemistry as a key step. Okay, so we come back to this these two strategies, the modification strategy and construction strategy. So we wondered whether we can merge these two strategies together in a net product synthesis. So shown here is a net product isolated from this very nice plant species. It's quite interesting that the net product contains an isoquinidine motif and two stereogenic centers, which are very far away from each other. So it's very difficult for the net product isolation chemist to determine the relative or absolute configuration of these two stereogenic centers. And I would like to mention Richmond Sapong recently also reported very, very elegant synthesis of this net product. So when we look at this structure, we think normally people will start from isoquinidine and try to build up the fine membrane and also put this linkage here. But we think maybe we can construct this pyridine motif, hopefully from this compound 4, this piperidine type of structure. And to synthesize this precursor 4, we would like to exploit the CH functionalization chemistry developed by Jinquan Yu using this triphthamide derivative group. I think that the interesting part of this chemistry is the triphthamide is not only serve as the derivative group for this CH bond formation, but also can serve as very nice handle for the Mies-Noble reaction. And also this triplet could undergo elimination to form the imine species, which can also help us to build this aromatic ring, this pyridine ring. So basically, this triphthamide can play 3 roles in our synthesis. So this kind of intermediate is fairly easy to prepare, but we still need to set the 2 stereocenters here. So we think about 2 different strategies. One is the asymmetric hydrogenation of this tetrasubstitute olefin, and another Of course, this one could be challenged because the catalyst and ligand design. And another quite interesting approach is the kinetic resolution. This chemistry also developed by Jin-Kuan Yu. If we can use this racemic substrate, which can be readily available from hydrogenation of this, just platinum on carbon hydrogenation of this intermediate. And then we run the kinetic resolution, we can obtain the two enantiomers. This is also very helpful because potentially we need to synthesize all four stereoisomers of this net product. Imagine if you only synthesize one or the proposed one, maybe you can't decide the absolute stereochemistry because all four stereoisomers could have the exactly same spectra because these two stereogenic centers are very far away from each other. Okay, so we look at the first approach, the hydrogenation. We quickly screen some ligands and then found my colleague Wenjun Tang's ligand shown here worked very well, gave us a pretty high yield and EE. And we quickly explored the scope of this chemistry. We found the non-functionalized tetrasubstrate olefin or the ester alcohol containing substrate also all perform quite well under these conditions, and sulfonamide also can be tolerated under these conditions. Okay, so we use the real system and it worked quite well. 98% yield and 91% EE. We do a recrystallization of the product, and we can get over 99% EE. And we use Jin-Kuan's standard conditions, and this reaction could be performed above 10 gram scale. So just one pod, we can easily prepare 10 grams, 20 grams of this compound 28. But we didn't stop here. We actually move on to the kinetic resolution. And this reaction also worked quite well using Jin-Kuan's monoprotected amino acid. We optimized condition a little bit. We found that the result is pretty good. The desired product could be obtained 46% yield, 97% EE. The other enantiomer, this compound here, the EE for this compound is slightly lower, but it doesn't matter. We can just throw it back into the kinetic resolution conditions using the opposite ligand, and then we can also get very high EE of that compound. And we also explore the scope of this transformation. We found this palladium-2 chemistry is quite robust. And for example, substrate with the bromide substrate survived here, and the TBS protection also can be tolerated. Normally the TBS on the phenol is not quite stable under either acidic or basic conditions. Acid also okay here, and the sulfur atom is also okay. And it's pretty interesting to see some substrate like here and here. So we can use this kinetic resolution to prepare enantiomer enriched sulfonamide with this quaternary center here. So basically the kinetic resolution just doesn't really care about this quaternary center or tertiary center. It just separate these two. So automatically we can generate this quaternary center containing product. Okay, then we test this reaction in the real system on 5 gram scale. Actually, we can also do on much larger scale. This reaction proceed very well to give us the desired compound, and this, as I mentioned, the opposite starting material can be subjected into the exactly same conditions, but use the opposite ligand, so we can obtain both compounds in nice EE. Okay, then with plenty of this compound in hand, we push forward, cleave this bond and make the alkyl mise-noble reaction work very well here. And we treat this compound with strong base. Presumably, we first generate a negative charge here, and that species undergo beta elimination to remove the trifluoride, and further oxidation at this position give us this compound in the end. And we quickly prepare this triplet, and the other fragment is prepared from this net product, and we put these two together to make the net product. We synthesize the 4 stereoisomers of this compound, and as we expected on the mass spectra, exactly the same. So we can't really differentiate these 4 compounds, but fortunately we have the 4 compounds in hand. We just make them together in a 1:1 to 1:1 ratio and separate the mixture from HPLC. And this is the authentic sample. And we run the HPLC again with the 4 synthetic samples, and then they completely determine the stereochemistry of the net product. All right, so I will quickly go to the last example. So that's quite different from the previous examples. So that's about a late stage CH oxidation. So the Hadlin type of a C20 diterpenoyl alkaloids is a very attractive class of molecules. A lot of chemists actually did nice studies, very elegant studies toward these molecule synthesis. And of course, from a more broad perspective, the C19, C18, C20 diterpenoyl alkaloids just have long been very attractive targets to synthetic chemists. So the Hadlin skeleton is like this, and the oxidation state of these molecules could be quite different, but we are particularly interested in this one, containing a secondary alcohol at here. So we hope we can do a this stage CH oxidation at this position, taking advantage of this ketone functionality, because we have that experience of Sanford oxidation using the oxime derived from this ketone. Okay, so first show you the retrosynthetic analysis of this molecule. When we look at this molecule, we think it could be quite straightforward to construct this polycyclic structure. You just view this molecule as a 2-layer structure. So it's just like a piece of cake. So the top layer is the red one, and the bottom layer is the blue one. And we hope we can use the Diels-Alder reaction to attach these 2 layers together. So the Diels-Alder substrate is shown here. And if we can form these 2 bonds, the 2-2-2 bicyclic system like this, and then we can run this stage CH oxidation at the C7 position. And the top layer could actually come from this tricyclic aromatic compound. And we hope we can use Carrera's Pauline cyclization initiated by the iridium, the chiral iridium complex. Then we can build up this compound 7 enantiomer selectively. And this compound could be prepared from this very simple building blocks. Okay, so I will just quickly go through this chemistry. We first prepare this ketone from guanine addition, and then form this tri-substituted olefin through Wittig reaction. So this MOM group is a very good handle for the geometry control. So that chemistry was developed by E.J. Corey. So we quickly prepare this Pauline precursor and use the Carrera catalytic system. We can make this compound. Unfortunately, the reduced activity of this, the last cyclization is not very good, 2-to-1 ratio. So that means we can't really control the selectivity, the position selectivity of the Friedel-Crafts cyclization that well. But fortunately, we can separate these two compounds after we protect the mom group, and the desired product was obtained with more than 99% EE. And after that, just burst reduction gave us this this cis membrane, and we quickly convert that compound in. Excuse me, convert this compound into the precursor for the Diels-Alder reaction. And this Diels-Alder reaction did not perform that well as we expected. We tried different things. So this is in situ formation of the in-mean species, which could serve as the die-in. And unfortunately, that expected Diels-Alder reaction didn't really happen. And we also prepared a stable cyclization ether species, which can be isolated. We heat it up until it decomposed. We didn't see any Diels-Alder product. We also tried the double Michael conditions. We get this alpha beta unsaturated enone, and we hope we can use the enolate from here to attack here, and then hopefully this enolate can attack back to form this bicyclic system. Unfortunately, this formal 4+2 reaction didn't work as well. Interestingly, when we treat this compound with base, we found this compound automatically undergo ionic Diels-Alder cyclization at 0 degree to give us this desired compound. And I would like to mention the dienophile here is not active by electron withdrawing group like in this case. So basically we can use electron almost neutral olefin as a dienophile, and we get a crystal structure of this compound. And after that, we quickly elaborate this compound into this intermediate. And oxime would serve as a handle for the CH oxidation, and this peroxide is actually a protecting group for this olefin. So we hope we can cleave this peroxide into the corresponding aldehyde after the CH oxidation. And we run this reaction actually after some optimizations of the conditions. We found we can obtain 42% yield of the desired compound. It's quite interesting. We only see the CH oxidation at the secondary position, but this methyl group is completely away from this oxidation. We get a crystal structure of analog of this oxime precursor. We found actually this methyl group, this O methyl point to the direction of this methyl, and lone pair of the oxime point to this position. So that geometry basically decide the palladium mediated oxidation will not touch this methyl group. And also, if you build up a model, you will find this this equatorial position is more accessible to the palladium for the palladium cycle to be generated. And therefore, we just obtained a single diastereomer of this secondary acetate. And after that, we cleave the epoxide into the corresponding aldehyde, and the methylation gave us this compound. Oh, forgot to mention, we have to use stoichiometric of this palladium in this particular case. It's not because of the Sanford chemistry. It's only because the stability of this peroxide. So we can't really leave this substrate in the reaction system for too long time. So we have to quickly quench this reaction after 1 hour. So in that case, we have to push this reaction faster. And also, for that reason, we recover 33% of the starting material. If we leave this compound too long time, the product too long time under the conditions, the acetic acid solvent can open up the epoxide and just mess up the product mixture. Okay, the end game of synthesis is fairly straightforward. We selected from the imine species with this aldehyde in the presence of this hydroxylamine, and then reduce the immune species selectively in the present to more hinder the ketone, and this secondary amine form will attack this ketone automatically to form this compound. And if you leave this compound neat at room temperature, it will just automatically cyclize to give us this heterocycle. So this is the model compound without the hydroxyl group. We just borrow this chemistry here with the real substrate, and the reaction work equally well to give us this desired net product. And we also get a crystal structure of the model compound, also the ester derivative of the desired net product shown here. So I would like to end here. Basically, I show a few stories how we try to utilize the CH functionalization chemistry in the synthesis of different net products, and hopefully we are really excited to see many new methods coming out, and really want to explore the applications of these methods in complex molecule combined with some interesting strategies. Okay, I would like to thank my collaborator Dean Tantillo and Dave Edmonds, and also the students who actually work on these projects, and also the funding agency for their support. I would like to take any questions you may have. Thank you so much.
So Ang Lee, thank you for a really wonderful talk, really demonstrating, really challenging CH functionalization. And that's really important. And it's great, the whole range of different types of reactions have come in. So I'd like to encourage people to give Ang Lee a round of applause. And yes, so a very positive response, as you can see. And there are already comments in the chat room and also questions for you, Ang. But because of the time, if you don't mind, we'll go on to the next talk. So if you could go to the chat room and answer those questions, if you answer them for everybody, then there could be more responses coming in as well. And
sure.
Thank you very much for making this great effort to join us at this time. That's really been great. Okay.